So what I will try to tell you today is a little bit different than what you heard so far. It would be really not how to characterize polymers, but how to make them. And I will start probably first with my self-introduction. I come from Pittsburgh, from Pennsylvania, from US. And Pittsburgh is in fact halfway between Chicago, what we heard from previous speakers, and New York, which you have heard from some other speakers as well. So Pittsburgh is in a delta of 3 rivers. This is Monongahela, Allegheny, and here Ohio River starts and then eventually goes to Mississippi and Mexican Bay and eventually to Corsica in some sense. So Pittsburgh is a city of maybe 1.5 million inhabitants. In delta of these 3 rivers, these are cities in a downtown. This is Pittsburgh plate glass building. Is probably the largest producer of chemicals in Pittsburgh. And PPG used to be maybe 5 years ago, 1/3 thin films, 1/3 chemicals, 1/3 glass, and now it is 100% thin films. Whether it would be thin films for automotive coatings or any kind of paintings, but also even for batteries, because it's rolled thin films in some sense. So I work in a Carnegie Mellon, and this is a Mellon Institute. The last director of the Mellon Institute before merger with Carnegie Tech was Paul Flory. In 1968, he left and moved to Stanford. At that time, this quite classical library there and some buildings for students' enjoyment. So some of you probably have never made a polymer. So this will be one slide introduction how you can make polymers. In general, 2 pathways. One is so-called step growth polymerization. This is the way you can make polyesters, polyamides, and also in principle proteins as well. This is very unusual situation because reactivity of the end group, whether it would be amino group in amino acids or in a dimer or in a trimer or in a polymer, is essentially the same. Because of that, you have always one elementary reaction which repeats over and over and over again. And molecular weight or degree of polymerization increases very slowly with conversion. It follows so-called Carover's equation, where X is fractional conversion. So at 50% conversion, 0.5, you have essentially dimers. At 90% conversion, you have decamers. And these are not polymers. In order to get a polymer, you need to go to 99, or sometimes 99.9, or sometimes even 99.999% conversion. So this takes really long time because it is reaction typically following second or third order kinetics in respect to monomer. And sometimes if you are organic chemist, if you get, let's say, yield 90%, you are extremely happy. 90% yield in polymer chemistry is a disaster because you can only make decamers. You can never make a high molecular weight polymer. So it's a very specific process. So in order to get molecular weight at a lower conversion, you can think about a chain growth reactions. In a chain growth process, monomer does not react with monomer. Monomer needs to be initiated by some kind of an initiator. It can be acid, base, organometallic species, or free radical. And then after generation of the first active center, it reacts very quickly with another monomer. Frequency of monomer addition may be in a range of milliseconds, sometimes even microseconds. So within 1 second time, you get huge molecular weight, degrees of polymerization, 1,000 or sometimes 100,000 even. And then molecular weight typically drops with conversion because you have chain breaking reaction, transfer and termination. So it is very difficult somehow to dial exact molecular weight because you have many elementary reactions. And approximately 60 years ago, Michael Schwartz developed so-called living polymerization. He was able to suppress these termination and transfer reactions. And if initiation is fast, In that case, all chains grow concurrently during polymerization, and molecular weight or degree of polymerization increases linearly with conversion. So if you have a ratio of monomer to initiator 100 to 1, at 50% conversion, degree of polymerization would be 50. At 80% conversion, 80. At 100, 100. And then you can add more monomer and continue to grow these chains. Or you can add another monomer and make a block copolymer. So at that time, it was really like a revolution in polymer science because nearly nobody before could make block copolymers because they hate each other. They macroscopically phase separate, but in a case of a block copolymers, they would phase separate on a nanoscale, on a scale of nanometers, essentially. So this was beginning of nanotechnology in some sense. Again, this equation, Caraver's equation, has a little bit different meaning. X is not conversion. X is a fraction of the chains which can continue to grow versus some other chains. So in order to get degree of polymerization 100, you need to have a 99% selectivity of propagation over chain breaking reactions. So now if you go to radical polymerization, what I will be talking to you about, approximately more than 1/3 of all polymers is produced by radical means. So this number, 100 million tons per year, it is 100 billion kilograms per year. So divided by 8 million people, it would be approximately 1 kilo per month per every person. And in fact, radical polymerization used to be more than 50%, but recent progress in polyolefins changed a little bit these proportions. So why radical polymerization? Because you have a very large range of monomers. Practically any compound with a double bond can be either homopolymerized or copolymerized by radical means. And you have on the market maybe 500 different metacrylates, methyl groups, so to make plexiglass, but also hydroxyethyl substituent, it will be HEMA, making contact lenses, sometimes combination with proteins, with nucleic acids, as you will see later, and so on. It's also very easy copolymerization. Reactivity ratios are close to unity, so you can make a myriads of different statistical copolymers plus block copolymers and some other complicated structures. But maybe industrially most important is very simply to run them. You can do it in bulk. This is how plexiglass is made. You can make it in solution. It can be organic solvent, can be water under homogeneous, but also dispersed media. So all of these emulsions, mini emulsions, microemulsions, dispersion polymerization go here. And typically you run reactions at maybe 60, 70 degrees. So you take a heat of a exothermic polymerization as such. And otherwise you can work at -80 if you wish, and polyethylene is made at 250 degrees. So large range of really conditions. However, the problem is that formally radical polymerization should not occur at all, because every encounter between two radicals is termination. And this encounter happens with diffusion control rates. So as quickly as two molecules can diffuse, they instantaneously terminate. So in order to suppress termination, one need to keep radical concentration very low, parts per million or parts per billion under some conditions. So how to do it? How to work with such a low concentration? Typically you dose radicals to a system continuously and slowly. If you take peroxide or take diazo compound like AIBN, it has a half-life time 10 hours, and every moment one radical is formed, it propagates, and after 1 second time, it terminates. And the new radical is born, propagates like crazy with a monomer frequency addition less than a millisecond, and then it's gone. So you cannot make block copolymers, you cannot make any functionalized structure. So it's impossible to control topology, end groups, or composition. If you look what happens in polymer science and maybe chemistry in a broader sense, industrially, people would like to make some value-added products, which means you take cheap monomers and convert them to gold, essentially. So how you can do that? There are many new compounds which are used this way, many new materials, smart materials, self-healing, as you have heard during these talks, many other things. But typically, you would need to have more and more inspiration coming very often from nature. So this would be really making materials which would either self-assembly or have certain type of a molecular recognition. And this would require some kind of a nanophase separated systems. What Michael Schwartz did in 1956, he invented this living polymerization and bulk copolymers. But this has to be done at temperatures minus 80 degrees, in complete absence of carbon dioxide or air, no moisture, down to really parts per billion removal of the moisture, because otherwise you will quench these reactions. So if you take advantages of this radical polymerization and some advantages of this living anionic or cationic polymerization, you can combine them together, and this was beginning more or less 20 years ago, how the controlled radical polymerization started. Whoops, sorry. So this is really beginning of the 90s when the research on controlled radical polymerization started. And if you look now where we stand, it is nearly 50,000 papers on controlled radical polymerization, a bit more than half on atom transfer radical process, which I will give you more detailed information. If you look at the Google and you put atom transfer radical polymerization, it would be more than 5 million entries. And concerning patents, on US Patent Office, 5,000 patents on controlled radical process, a little bit more than half on ATRP. If you go to Google patents, you will type atom transfer radical polymerization, it is 170,000 patents and patent applications worldwide, not US only, but many of them in China and of course different parts of the world as well. So some years ago, Bob Matson from DuPont estimated that it would be a market around $20 billion a year, which at that time corresponded to maybe 10% of all radical polymerization market. But this is 10% not by volume, but 10% by market share. So no commodities, but high specialties such as coatings, adhesives, surfactants, dispersants, lubricants, gels, cosmetics, hybrid materials, nanocomposites, electronic, biomaterials. And of course, in 21st century, we need to think about sustainability, about recycling, some renewable resources, and so on. So what is the difference between conventional and controlled radical polymerization? Intermediates are essentially the same. You have these free radicals. And if you look at these three reactions as propagation or initiation, propagation, termination, they are essentially the same here and there. The only difference is that here you generate these radicals irreversibly and very slowly. So half-life time of a radical initiator is approximately 10 hours. And here you generate radicals reversibly at both initiation stage and also at propagation. And this makes dramatic difference. You remember this high molecular weight at the very beginning in a second, and then dropping down with conversion, high dispersity. And here all chains grow concurrently with conversion, having very low molecular weight distribution and very high uniformity. So if you inject these samples on GPC, this is a GPC standard, this is ATRP-made polymer, and this is conventional free radical polymerization. So very, very, very different. So one thing which you need to know, that we would like sometimes to run the reaction fast, but if radical concentration would be higher, in that case termination will be also higher, not only propagation. This is first order reaction in respect to radical concentration. This is second order reaction. So in principle, you cannot run them very, very fast because you will have too many radicals. They would terminate too quickly, and you need to scale somehow time of the reaction with conversion, with the ratio of termination to propagation coefficients, targeted degree of polymerization, and the fraction of dead chains you can tolerate, whether it will be 1% or 5% or 10%. All of that depends, in fact, very much on nature of monomers. If you look at termination coefficients, they practically terminate with nearly the same rate coefficients. It's a diffusion control process. It depends on a chain length, it depends on conversion as well, because it depends on the amount of the polymer. But propagation rate coefficients are pretty dramatically different. You could see here that methyl acrylate would propagate approximately 30 times faster than methyl methacrylate, and additional maybe twice faster than styrene, which means that you can, at the same reaction time, you can have much less terminated chains for methyl acrylate or for acrylamides or acrylate polymerization, essentially it would be 30 times 30, so 1,000 times less terminated chains. So therefore, if you would like to have a, let's say, degree of polymerization 100 at 90% conversion with 90% preserved chain end functionality, you can run this reaction at 60 or 90% conversion within seconds. But here you need hours or maybe even days. So this is important. If you would do these experiments, you need to know what kind of monomer you have, what propagation rate coefficients you have, and how to control these reactions. So in principle, you may say that you need low radical concentration in order to have controlled radical process. But in reality, it's not only radical concentration, but it's a fraction of terminated chains. So for what I showed you, acrylates or acrylamides, you can have still fast reactions and very few terminated chains. So if you have a below 1%, I think you should be happy, 99% preservation of the chain ends, 99% of a block copolymerization yield. And another very important issue is that you would like to extend life of propagating chains from seconds to hours, just to make these synthetic manipulations much easier. So conventional radical process is slowly initiated, and after 1 second, all chains are terminated, essentially. And here we would like to extend it to maybe hours or maybe even days. This can be done by really equilibrating these free radical propagating species with various types of a dormant species. Dormant, which means that they are sleeping, essentially. They cannot terminate, they cannot propagate. And this bond here between chain end and this capping agent is pretty weak. So therefore, this bond can homolytically cleave and regenerate this radical and counter-radical. This radical can propagate maybe once or twice, and then it will be converted from the active to the dormant state. So what kind of a bond, weak bond may be here? You can use something which would be, I will show you some examples, like alkoxyamine, or this can be nitroxide, for example, tampon. It can be also organometallic species, even close to biological system, like vitamin B12. So it's a carbon-cobalt porphyrin bond, which is very weak and labile. You can also have a catalytic process, because here you need every chain end capped with this species. Sometimes, if you think about cobalt porphyrin, it may be pretty expensive. So why not to use, for example, bromine or chlorine? Unfortunately, this bond is too strong, and you would need to work at maybe 300 degrees to break this bond with a sufficient frequency. So many side reactions, energy extensive, nobody would do that. So can we use a catalyst which would lower activation energy from, say, 60 kilocalories per mole to maybe 10 or maybe 5, and you can work at room temperature in an efficient way? So these compounds typically will be organometallic species, or can be sometimes the transition metals like copper or iron or ruthenium, as you will see later, and we call it atom transfer radical process. There is also another possibility, so-called degenerate transfer. So here you could see that equilibrium is very strongly shifted toward dormant species. Equilibrium constant may be 10 to the power minus 9, 10 to the power minus 5, and here equilibrium constant is 1. So whatever you have on the left side and right side is exactly the same. You just reshuffle this atom or group between these chains, so this one will become itself dormant and would activate this species, which can propagate once or twice and go back to a dormant state. So in all of these systems, if you want to have a control, proper control, you need to allow propagation maybe 1, 2, maybe 5 times, and then convert it to a dormant state. It would be the same here, maybe 1 or 2 monomer additions, and then conversion by exchange from active to a dormant state. So I will show you some examples of these systems, including alkyl iodide, sometimes derivatives of tellurium or bismuth. And now probably one of the most important things is ditio compounds, ditio esters, or xanthates. These are so-called Raft polymerization reagents. Another very important issue is that you need to have a fast initiation because you would like to grow all chains at the same time. In a conventional radical process, you have a very slow initiation. Half-lifetime is of initiator 10 hours, which means that you have a so-called steady state in conventional process. As fast as you initiate, as fast you terminate. You want to terminate 1,000 times slower than propagation, therefore initiation should be also 1,000 times slower. So no control, no block of polymers, no stars, no bioconjugates, or any kind of organic-inorganic hybrids. Here is a different story in this equilibration process because you establish radical concentration by activation, deactivation. And because of that, you are completely independent of this termination process. Propagation is still 1,000 times faster than termination, but initiation can be even faster than propagation. So if I take an initiator which contains 5 functional groups, in a radical process, conventional one, I would try to make a star, but I will make a one arm here, one arm there, one somewhere else. I could never make a star. In this control process, I will progressively grow all of the chains, and they will give me a star-like structure or bottle brush-like structure or bioconjugate, organic-inorganic hybrids, and some other fancy stuff. So here, if you look at this process, you take really 1 second life of a propagating radical, and you chop it on 1,000 pieces, 1 millisecond each, and then insert between every millisecond 1 minute dormancy state. So this 1 second is still 1,000 milliseconds plus 1,000 minutes. So it's a day. You have enough time to really make very fancy, sometimes molecular architecture. So one interesting issue is really so-called persistent radical effect. Because for many years, it was a puzzle how you can control this polymerization with nitroxide. So some people assumed that there was no termination of radicals, but in fact, it was a very different process because you have a bond which is broken homolytically. This can terminate, but this is persistent radical, and it cannot terminate. So it would progressively accumulate. So at the beginning of the reaction, you will form both the propagating radical and this capping radical. And at a certain moment, once you have a sufficient concentration of radicals, they would start terminating, decreasing their concentration, and the other one will increase. Because the product of concentration of this X dot and R dot should be equal to Rx concentration. So this is a very unusual situation. It follows a pattern. You could see here it's a log-log scale. So what happens here, this is essentially 10 seconds. This is 3 hours. This is 3 months. And this is 300 years. So it's a log scale. It looks really like a straight line. But on a linear scale, you would see that concentration of radicals will jump and then practically become constant. And this persistent radical concentration will progressively increase. X dot cannot terminate. They are stable radicals. You can buy them. So this is like, you will see examples like nitroxide or even this cobalt porphyrin. It is a paramagnetic species which is stable because it's stabilized by some steric effects and electronic effects. And you can really buy it from Aldrich or Sigma. They are stable. So they cannot terminate themselves, but they cross-terminate. And this rate constant of cross-termination is practically also diffusion controlled. If it would be slow, you would have a poor control. So you would like to have it as fast as possible, but only with this carbon-based radical, propagating radical, not with itself. Any other questions?
So you said that all of the polymers change the gradient at the same time.
Yeah.
Don't we have a low concentration of radicals?
Yes. But you have a large population. Concentration of radicals in conventional, in control process may be the same. But fraction of terminated chains in conventional is 100%. Nearly all of them are terminated, except this tiny amount of them which propagate. And here you have 99.9% of chains which are dormant. They cannot terminate. but they would grow in a periodic way. They will be reactivated, added 1 to monomer units, and going back to sleep. 1 to monomer units, back to sleep. So I will give you some examples of these reactions. So one of the probably the simplest is really with alkyl iodides. It is not a very good system, but it's somehow working. And you could see here what happens. You take alkyl iodide, which resembles propagating chain end. So this is really structure of a propagating polymethyl methacrylate. And this radical will take this iodine atom, become itself inactive, dormant, and activate this species, which can propagate couple times before being exchanged again. So the problem with this alkyl iodide is a very simple system because it would be degenerate transfer. Whatever you have on the left side is the same as on the right side. The problem is that it is not fast enough, which means that the ratio of a propagation to exchange reaction is very comparable to unity. Because this reaction, the exchange will be bimolecular with another alkyl iodide, and alkyl iodide will be at concentration 100 times slower than monomer. It means that you would add 100 monomer units before you exchange. So you don't go 1, 2, 3, 4, 5, you go 100, 200, 300, so molecular weight distribution will be much, much broader. So in 1998, in Australia, they developed a process which is called Raft, or Reversible Addition Fragmentation Chain Transfer Process. And now this species, which contain this double bond, this is sulfur-carbon bond, is much more reactive towards radical. So you could see here that now this exchange reaction is 100 times faster than propagation. So if I keep concentration of monomer to chain transfer agent, 100 to 1, I would add 1, 2, 3, 4, 5, and all chains would grow perfectly with conversion, and dispersities can be 1.1 or sometimes even less. So I will show you some examples how to select Raft reagent, because what is important on one side is that this bond should be reactive, so it should be stabilized by this group Z, which are listed here. But also, once you add this radical, you don't want this persistent radical to be stable too much because it can terminate with another radical. So you want to fragmentate it, and rate of fragmentation would depend on the leaving group ability. So from a point of view of stabilization, the phenyl group would be best, then tritiocarbonate, then some alkyl ditioesters, then xanthates, then diethiocarbamate. So this would depend what kind of monomer you want to polymerize. For MMA, if you would this, they would not work because they would propagate 100 times before exchange. If you would use, on the other hand, for vinyl acetate this one, it would form persistent radical, it would not propagate at all. Also, it would depend on this leaving group. So this is designing of initiator, very important for making block copolymers. So what kind of the order of monomers should be there? So generally, if you have a larger substituents, it's better. If you have groups which would stabilize radical, like cyano or phenyl, it would be also better. So this again, this would be good for methyl methacrylate, this would be good for vinyl acetate. So you need to have a certain selectivity there. Now, this is a slide taken from a review a couple of years ago, but you could see how these things progressively develop. You start first making this ditio compound, then you make a block of polymers, then stars, then brushes, then some kind of a micellar structure. You need to understand better mechanism of these reactions, and eventually go to bioconjugate complexes with DNA, nucleic acid, and sometimes organic and inorganic hybrids as well. One difficulty in Raft is such that typically you would need to add extra radical in order to propagate these species, because radicals have to be somehow generated. So very often people are using AIBN as a slowly decomposing initiator, which would run this reaction. But also this would give you additional chains. So if you want to make this 5-arm star, you will have a little bit of a 1-arm star generated from this AIBN. So it's a question how much you can tolerate, or how can you generate them spontaneously. So one approach is that you could use, for example, some copper as a catalyst to generate these radicals without generating new chains. So it would help photodissociation. And there is also some photo electron or energy transfer reactions, which under irradiation can also break this bond here and generate radicals without making new chains. Now, another approach, and this is related to your question about stable radicals, is nitroxide-mediated system. So the first example is so-called TEMPO, or tetramethyl piperidinial oxiderivative. So you can buy it from Aldrich, maybe $10 a gram or maybe $20 a gram. And this bond is unfortunately a little bit too stable for polymerizing acrylates or acrylamides. And there was another development of this type of, by, in fact, French chemist, by Paul Tordeau at Marseille, and also Yves Niano at that time at Bordeaux. And this compound is called, for abbreviation, SG1. SG1 stands for Sandra Grimaldi, her first nitroxyl radical she made at Marseille University. And then her whole PhD was to make SG2, SG5, SG10, SG20. SG1 was the best. So sometimes it happens that you are lucky when you do the first reaction, something works, gives you motivation to explore structure-property relationship, but SG1 so far is the best. So this is really a stable radical because it's stabilized by this phosphorus compound and these T-butyl groups. They change this ethoxy to methoxy, isopropoxy. Nothing was working as good as this SG1 original one. So under some conditions, you can have also pretty good control. Molecular weights follow this linear development with conversion, and dispersities go down to 1.1 or less. Now, the third system, historically probably the second or first, is atom transfer radical process. So you start with this inexpensive alkyl halide. They usually mimic structure of a dormant species. And then you add transition metals, such as derivatives of copper, iron, ruthenium, nickel, palladium, rhodium, sometimes also iridium can be used. And you need some ligands which would stabilize these radicals. They would like to be really sometimes electron donating, as you will see, radicals which would really favor formation of the sufficient concentration of radicals. And rate would depend on this equilibrium constant or ratio of these two rate coefficients, on concentration of alkyl halide, transition metal complexes. And these activation, deactivation processes depend very strongly on the nature of monomer, sometimes also on a reaction conditions, which means temperature and solvent, and also they will depend on the particular catalytic system. So how these reactions do occur? I will show you later what happens in the sense of a chemistry and transition state, but typically it goes via inner sphere electron transfer process. So it happens that this alkyl halide will approach the copper complex, and in transition state, this bromine will bridge between carbon and copper, and eventually will oxidize copper 1 to copper 2 and form a radical. This radical can be involved in 3 different reactions. Radicals can obviously terminate, they can propagate, and every act of termination will accumulate this persistent radical. So we'll have a higher and higher concentration of this copper 2, and then this radical, instead of termination, will have a cross termination or taking this halogen atom, converting back to a dormant state. So this typically happens, it's an example from bulk polymerization of styrene, so no solvent, 110 degrees above glass transition temperature. And if you look at the rate of polymerization, it shows you this ratio of activation, deactivation rate constants, and also a ratio of copper 1 to copper 2. So formally, rate of polymerization should not depend on a concentration of copper, but only on a ratio of copper 1 to copper 2. So if you can keep ratio the same, you can reduce amount of copper 10 times, 100 times, 1,000 times, million times. You should have the same rate of polymerization. So why do you need copper? You need copper to send this radical from propagating stage to a dormant state fast enough. And dispersity here shows that this depends on a reciprocal concentration of copper 2. So I need certain concentration of copper-2 in order to have polymers with low dispersity. For example, if I want to make a polystyrene 10,000 at 90% conversion, dispersity 1.2, 5 ppm of copper is enough. But if you would run this reaction at 5 ppm, a little bit of termination will completely stop the reaction. So you need to solve a problem like that. Maybe a little bit about this frequency of these reactions. So normally, if you think about the frequency of chemical reaction, you can take reciprocal concentration of a rate constant. For bimolecular reaction, it would be a product of this rate constant and concentration of the other reagent. So how quickly I activate this polystyrene dormant chain end? I look at the rate constant of activation, 5 10 to minus 1, concentration of activator, 10 to minus 1, product, 5 10 to minus 2, reciprocal value, 20 seconds. So every 20 seconds, chains wakes up. And it can propagate or deactivate or terminate. I can do exactly the same math, and it looks like under these conditions, I deactivate 6 times faster than I propagate, which means I activate, deactivate. 6 times, 1 addition. 6 times, 1 addition. 6 times, 1 addition, which is a little bit unproductive because I don't need that. So if I take another system, if I look, for example, methyl acrylate and another ligand, copper PM-theta, chain wakes up every 5 minutes, adds 14 monomer units, but dies after 1 month. So it would be 15, 30, 45, 60 on average, as such. Now, if you look at that, in this case of styrene, chain wakes up every 20 seconds, but add monomer 6 times slower, so every 2 minutes, and it will be essentially to get DP100, I would need 200 minutes, 3 hours, and it dies after 30 hours. So these are just examples to give you a little bit feeling how these reactions can occur. So going deeper to atom transfer radical process. So we develop now catalysts which are 1 billion times more active than originally used. So they are really extremely powerful, and therefore you can work now with parts per million of copper. We borrowed this atom transfer radical polymerization from organic chemists which use atom transfer radical addition. They worked at 10 mol% concentration versus monomer. So we worked at 1 mol%, then 0.1, and now we work really with parts per million. However, if you would have such a small concentration of radicals, even if they can exchange very fast to control polymerization, every act of termination will convert these activators to deactivators, reaction would stop. So in order to run the reaction to higher conversion, I need to regenerate these activators. And this is done in the presence of very mild reducing agent. Can be used something like ascorbic acid, can be even a little bit of a sugar, maybe iron. You can use also external field, electrical current, light, sometimes mechanical forces. You can run these reactions without solvents, sometimes in water. As I mentioned, can be heterogeneous, homogeneous system. And of course, the point is not to make homopolymers. The point is to make some complex molecular architecture, whether it would be something resembling these hairy colloidal structures. You will see later some molecular brushes and some bioconjugates here, growing polymers from the surfaces of even liquid metals, but also surfaces of any nanoparticles, or from flat surfaces, dramatically changing lubricity and friction coefficients. So of course, I think that the dream of every chemist is to make something useful. And we are very lucky, in fact, to sign 17 industrial licenses, and some materials made by atom transfer radical polymerization are produced in Europe, in US, also in Japan. And we interacted with 60 companies through ATRP, CRP consortia, having twice-a-year meetings. And I must tell you that students are extremely happy that they can sometimes discuss with people from industry and give them even advice how to run the reaction, because they know much more, because they have a knowledge of 25 years of doing this ATRP. I mean, build up knowledge. So what is the scope of a controlled radical polymerization? In some sense, we would like to dial whatever molecular weight or degree of polymerization we want. So you can make dimers by atom transfer radical addition, and typically we go to millions molecular weight. There are some cases of maybe tens of millions as well. And we would like to have a really predetermined molecular weight by a ratio of converted monomer to initiator, and also controlling dispersity. You could see here how narrow molecular weight distribution it is here, but sometimes you would like to make it broader, meaning that you can design molecular weight distribution. Sometimes you want to have maybe bimodal. Some low molar mass can act as a plasticizer and some high molecular weight as reinforcing material. So you can draw molecular weight distribution. Sometimes for block copolymers can give you also access to new morphologies. So typically we take monomers which contain substituents which would stabilize radicals. So this would be like nitrile group for acrylonitrile, ester groups for methacrylates or acrylamides, but also benzylic structure. Typically we would use organic solvents, sometimes water, as I mentioned, variable temperature, pressures, and I will show you also that we can tolerate oxygen, which is normally extremely challenging for any radical polymerization. We typically select initiators which would mimic dormant chain ends. So this would be secondary bromopropionate for acrylates. This would be isobutyrate for the methacrylates, and I will show you some examples how different reactivities they have. And then I will show you also some example of these catalysts or ligands which are used. So you can, by using DFT or some ab initio calculations, you can measure what is a bond dissociation energy between this carbon and bromine, or what would be stability of a radical formed. And these are really spanning many orders of magnitude. So if you look here, for the acrylates, this would be styrene, this would be methacrylates, this would be acrylonitrile, vinyl acetate, or even ethylene. Probably more important is not only equilibrium constant or bond dissociation energy, but also how fast propagation would occur. So it would be a product of equilibrium constant and rate constant of propagation. So if under some conditions I have the same catalyst, same reaction temperature, everything identical, if I would polymerize methyl acrylate within 1 hour, I would need 11 hours for styrene. I would have a half a second nearly explosion for acrylonitrile. It would take me 15 years for vinyl acetate and 170,000 years for ethylene, which means obviously I cannot use the same catalyst. I need to change catalyst and I need to develop new catalytic systems which are billion times more active. So how you can evaluate this catalyst? This is in fact a very, I would say, unusually accurate correlation between ATRP equilibrium constant, or a fraction of radicals which you generate, versus electrochemical potential of this catalyst. And in electrochemistry, 59 millivolts is 1 order of magnitude, or 1 decade of the values of the activity. So this spans, as you could see here, approximately 600 millivolts, so it is 10 orders of magnitude. So these are species which were originally used, pretty unreactive. Then we progressively make them more and more reactive, and now we have species which are really billion times more active than originally, meaning we can use less copper, extend range of monomers, work under milder conditions, sometimes going to iron, which would be environmentally and cost-wise also more interesting, and having additional advantages which are shown here. So one slide about how really these reactions work, because it's important to understand the mechanism that this transformation of alkyl halide with copper 1 to a radical and copper 2 can occur either via this inner sphere electron transfer process with a bridge intermediate, bromine between carbon and copper, but also can occur via outer sphere electron transfer process, via radical anions, and also concerted process and sometimes oxidative addition. So you can calculate this kinetic pathway, how fast they are, and if you look here at this activation energy, this is what is inner sphere electron transfer process, and the next step, this concerted structure, is 15 kilocalories per mole more. 15 kilocalories per mole more would indicate that if this half-life time of the activation would be 1 second, this would be 10 to the power 11 seconds, which means it would be 3,000 years. And this would be the time of the universe, more or less. Now, the transition state, which is the highest really at this, on this trajectory, highest energy point, is very late. It means that it would resemble products rather than substrate. And it's also very unusual because you could see that this is not straight, it's bent. There are some electrostatic attraction between negatively charged part of the acrylate and this positively charged copper species. So you can, by really looking also at the transition state, it would be highly developed spin and charge, so it is really looking like a product nearly. So this is really how it happens, that the alkyl halide will come from a little bit from the side of this copper and then transfer this bromine through the transition state, which is one vibration essentially, and then can be reversibly activated and deactivated. How I'm doing on time? Okay. Yeah, maybe I can skip some of these parts and tell you a little bit about really how you can go to the designing of a new catalyst. So you have many ligands. They are nitrogen-based, most active in fact. And it looks like the distance between carbon atoms, between two different nitrogen atoms, the better 4 than 3 than 2. Also, if you look at the, this is number of nitrogen atoms. This is the carbon bridge. 2 is better than 3 than 4. Typically, we want to have a branch structures, and then pyridine or alkylamines. So these champions, these are circled in red, they practically take all of these already structural features. So how we can go further on? And in fact, one possibility is to put electron-donating substituents. So you could see here what happens if I would put this pyridine containing dimethyl methoxy substituents, and now if I put one of this group, it becomes 10 times more active, 200 times, 1,000 times. If I go to dimethyl amino group, it becomes 10,000 times more active. So this is the way how you can go to this more active system. So we are working with really systems which can be decreasing concentration of copper from 1,000 ppm to 10 ppm. You could look at this reaction mixture. If you go to 1 ppm, for many applications, you don't need to remove copper. For some, you still need to remove it, for example, for biological systems by dialysis. But if you have a system which is so active, but if you use such a low concentration of copper, I mentioned to you that every act of termination will convert these activators to deactivators irreversibly, and the reaction would stop. So I need to regenerate it using various reducing agents. And these can be chemical compounds. For example, ascorbic acid can be also diazo compound or peroxide or tin octoate. You can have in that case, sulfides, which are used in food or wine preservation. You can have also a piece of copper or iron wire. You can plug in electricity and control it either galvanostatically or potentiostatically. You can use light, you can use mechanical forces, typically generating piezoelectric system. However, very important is that if you stop reducing or incorporating this reducing agent, if you stop feeding ascorbic acid to a system, reaction would stop nearly instantaneously. So normally in a radical polymerization with exothermic, it is dangerous because sometimes you build up so much heat, and this heat can decompose more initiator, and reactions run away. So it is really Tromsdorf effect, or sometimes called gel effect, which can be fatal. So typically every couple of years, polyethylene high pressure plant just blows up. But here it would never happen, because if you stop feeding this reducing agent or switch the electrical current or switch the light off, reaction stops because you cannot regenerate these activators anymore. So I will show you maybe one example of the electrochemical process. So electrochemistry is very environmentally friendly process. And we started really copying the classical setup for electrochemistry, meaning that we have a working electrode, which was a platinum mesh. It was a counter electrode, fritted with to separate really this compartment, and also a reference electrode. And this was done under potential static conditions. Progressively, we improved the system by replacing this expensive platinum by stainless steel or glassy carbon or nickel chromium. And you can use here sacrificial aluminum wire, no separation needed, no reference needed. You can run it under galvanostatic conditions. So no potential stat, you can have a battery essentially to run this reaction. If you look at the principle of electrochemistry, the applied potential should control a ratio of this copper 1 to copper 2, which means it would control the amount of radicals. If I have more copper 1, I have more radicals. If I have more copper 2, I stop the reaction. So by changing potential, I can really control the rate of the reaction pretty precisely. So here's an example. If you take cyclic voltammogram of this copper complex, if I am at sufficiently positive potential, there is no electron flow, so there is no polymerization, reaction stops. If I go to more and more negative potential, then I generate more and more activators, and polymerization would start, and then I can go back. So here is an example changing from negative 400 to negative 700 potential. Negative 400, nothing. 700 starts. I go back to 400, stops, starts, stops. I can climb to whatever conversion I want. And here you could see this molecular weight evolving with conversion, dispersity going to values 1.05, like in anionic polymerization, if you wish. Entire molar mass distribution shifts to higher values. So now there is a kind of a question. Can I go to more and more negative potential and potentially getting faster reaction? And there is a problem. If I go to more and more negative potential, now you could see that reaction here essentially would stop. And on a platinum electrode, I have deposition of copper, and there is no more copper catalyst in the reaction mixture. Reaction stops. So this is bad news. But also it's a good news because I can remove copper this way. And now if I would go back to the very positive potential, I can strip this copper and put it back to solution, and then I can recycle that. And if I go to original potential, I have the same rate of polymerization, same molecular weight, same dispersity, and you can remove maybe 98% of copper this way and strip it back probably with over 90% efficiency. So this is really very unusual way that by changing potential, you can also stop the reaction, restart the reaction, and remove copper, which would be important for some applications. Another interesting, sorry.
Does the amount of copper you can remove from the reaction depends on the surface area available, or is it independent of?
Yes, you can have a surface area of the electrode much larger, so you can have a multiple electrodes potential as well. You know, typically we work with a low concentration of copper, so we work with a 5-10 ppm of copper, so this is really not that much. But you can remove it because it will be electrodeposited. Copper will be conductive material, so you can electrodeposit it very efficiently. Something interesting extension of this electrochemical process is really using piezoelectricity. So there are some species based like barium titanate or zinc oxide, which generate under ultrasound or mechanical forces, will generate the positive charge on the surface, and in that case it can attract copper, and eventually you will have a reduction of a copper 2 to copper 1 and starting the reaction. So if you switch this piezoelectric effect of switch ultrasound off, there is no polymerization, on, off, on, off, on, off, on, off, and you can climb to also whatever molecular weight you want with low dispersities. If you switch from barium titanate, which was original work, to the zinc oxide, we work now with a zinc oxide 5 nanometers only, stabilized by octylamine, and you can have a concentration of the zinc oxide 0.06 weight% in comparison with 5 weight% for barium titanate. So it works pretty nicely, and we wanted to extend it further to using even lower and lower concentration of zinc oxide. So we went from this let's say, 0.06 weight% to 0.1% to 0.001%. Eventually, in water, we went to 0, no zinc oxide, and the reaction was still working. Because ultrasound, in the presence of water and small amount of the oxygen, can generate hydrogen peroxide, which would generate hydroxy radicals. So you don't need these piezoelectric particles at all, but these hydroxy radicals will generate new chains, radicals, which would reduce copper-2 to copper-1 by taking this halogen atom and generating corresponding species of the activators. So ultrasound on, off, on, off, on, off, on, off. So it is also very important that because you work with such a low concentration of copper, it's enough to switch it off and polymerization stops. So it's a very good temporal control. But if you want for spatial control, you can use to some degree electrochemistry, but it's better to use photochemistry. Here's an example of a feeding of the ascorbic acid. So ascorbic acid is used in this system at a very low concentration. So it is fed at a concentration approximately 16 nanomolar. But in water, you have to be aware of one reaction, that this copper-halogen bond is highly dissociated. What we call halidophilicity, or affinity of the halide towards copper-2 species, in organic solvent is 1 million equilibrium constant. In water, only 10. So this is highly dissociated, and you don't have a deactivator to control polymerization. So by using Le Chatelier principle, you can add a little bit of a salt, sodium chloride, sodium bromide, and now you have enough deactivators, so we use sodium chloride 30 millimolar, and polymerization is very well controlled, good control of molar masses. You can make block of polymers and control the reaction properly. So light is another very easy to control the reaction, and here we are using, yes?
When you do these reactions like the ultrasound one, and water, do you have to worry about dissolved gases like oxygen?
You will see later what to do with oxygen. So in fact, some of these reducing agents, they consume oxygen as well. So for many years, oxygen was the most powerful inhibitor of radical polymerization. You need to bubble nitrogen or work under, just inert atmosphere in a glove box and so on. Now we can use some light, and it works like a charm. So you can work really in a completely open atmosphere. So for light, what you need, in fact, you need to excite copper-2 to excited state species, and then you need an electron donor which can donate electron in order to reduce copper-2 to copper-1 and produce activators. So with the red light, it doesn't work because copper complexes do not absorb efficiently in these values of energy or light wavelength. But with a blue here, you could see faster, with a violet even faster. If you do on a sunny way, like at the Cargese today, it would be very fast reaction because you have a lot of sun. This is rooftop of Mellon Institute in a sunny day. And you could see that this was really like a on-off, 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 and molecular weight were nicely controlled with low polydispersity. So you can do these reactions, in fact, also in water. Reactions in that case for the water-soluble methacrylates, and applying light, you need to think about this halidophilicity. So we add a little bit salt. Without salt, high dispersity. With salt, dispersity 1.1, 1.2. So just really a few drops of sodium chloride, and it should work very nicely. This is in fact probably the simplest system you could think of, because normally we need a monomer, we need a catalyst, and we need an initiator. And here we work without initiator, because what happens here, this iron tribromide will react in the presence of light with methyl methacrylate and form this 1,2-dibromoadduct. So it would generate initiator in situ. And if you have a more iron tribromide, which will be progressively reduced to these activators iron 2 species, in that case, you will see induction period, because you need to reduce approximately 85% of iron 3 to iron 2 to start the reaction. Once it starts, meanwhile, it produces initiator, and if produces here longer induction period, more initiator, shorter chains, lower molecular weight. So it's really the simplest way you could think of: light, monomer, and iron tribromide, three inexpensive species, and you can make block copolymers this way. Back to your question about oxygen. So oxygen is really an inhibitor which is extremely powerful because it forms peroxy radicals which react with monomer very, 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 very slowly. So practically no polymerization. In a case of this on-top transfer radical process with copper, it's even worse because these species are strongly reducing. So they will react with oxygen and oxidize themselves nearly instantaneously, these most reactive species. Sometimes you can use that process in order to produce electrochemically hydrogen peroxide. So use these copper complexes which work really very, very nicely. So how to improve this system? In some sense, how to make oxygen-tolerant radical polymerization. There are some examples on the atom transfer radical process, on Raft process, but very interesting, in fact, it's also enzymatic process. So first it was used by Professor Yakchi, who used glucose oxidase and glucose for free radical polymerization. And you could run the reaction in an open air, but you need to have an enzyme and you need a glucose together. So can one do something similar in a controlled radical process? And in fact, you can do that because the product, hydrogen peroxide, is not a good radical initiator. Which means that if you run a Raft polymerization with these diethyl compounds, you can have these pentafunctional initiators and you will not generate new chains, you would form just a star or bioconjugate or something else. Again, problem with ATRP is that you have these copper complexes which can react with hydrogen peroxide in a phantom-like reaction. The most known phantom is really iron, two species being oxidized to iron 3. Here, copper 1 will oxidize to copper 2 and produce hydroxy radicals. Hydroxy radicals will generate new chains. So now if I want to make a pentafunctional star, I will make a star, I will make linear chains. If I want to go to degree of polymerization 800 with this alkyl halide, I will produce 4 times as many new chains and molar mass is only 200. So what to do? So you can go back to maybe biochemistry book, and you could see that the sodium pyruvate is used in a Krebs respiration cycle or cell respiration cycle. So pyruvate reacts very quickly with hydrogen peroxide, and they would form carbon dioxide, water, and acetate anions. So this is very similar to breathing process because we work with these reactions in the open air. Oxygen comes in, CO2 gets out. Oxygen comes in, CO2 gets out in the presence of pyruvate. And now if I want to make a 800 dP, I make 800 dP. If I want to make a star, I make a star, or bioconjugate, or organic-inorganic hybrid. So this all is now possible with this pyruvate system. But you are contaminated with glucose and glucose oxidase. So can we replace this glucose oxidase with something else? And in fact, you could do it with light. So I mentioned to you before that this bromidophilicity, or fixing bromide on copper 2, is reversible. And now you have another anion, you have a pyruvate anion, and you form copper 2 pyruvate, which is light sensitive. And it's enough to irradiate it with light, reduce copper 2 to copper 1, so you regenerate activators, produce pyruvate radicals, which very quickly decarboxylate, form acyl radicals, which are not efficient initiators. So now you can work in a completely open-to-air atmosphere. You need violet light to activate this system. And you could see it takes 15 minutes to purge this oxygen by itself because you have oxygen concentration sufficiently high. Then polymerization starts, and you could see open vial, 30 minutes, and this capped vial, 30 minutes, very similar results. So this is nice. But we sometimes would like to make it also very simple, so everything is done in a completely open air. You can have syringes with your monomer and copper cocktail, if you wish, and then you plug it in, vortex it, and eventually put it in a reactor with a violet light, and polymerization starts this way. So this can be done for different monomers, not only water-soluble monomers, but you can do it also in organic solvents like DMSO or DMF, and this is range of monomers, low dispersity, good control of molecular weights. Now, one issue is violet light is for biomolecules a kind of a problematic. So you can do it for short time, not high intensity. So can we go to green light, or can we go to red light or infrared light? So this tells me that probably I can use different types of the photo ATRP. One approach is what I showed you already before, that you can use this copper-2 species, which can get photoexcited, and then in the presence of electron donor, reduce to copper-1, and then you have a classical ATRP equilibrium. These complexes, they are very, in fact, reducing. They have a redox potential negative 300 millivolts. Now, you have some other species, especially organic, so some people would not like to use any transition metal. For example, you could use phenothiazine or phenoxazine and acridins. They can be photoexcited to a redox potentials in a range of negative 2 volts. So 2 volts versus this one is like 10 to the power 20 or 30 times more active. So they are so crazy reactive when they donate electron to anything, also to alkyl halides. So in that case, you can have a reaction of this photoexcited species with alkyl halide, reduce it to radical, in a kind of a magic way gets deactivated somehow. The problem is that lifetime of these photoexcited species are nanoseconds, or sometimes picoseconds. So you don't have them at a very high concentration, because otherwise you will have too many radicals. And then you have another class of species which would be also photoexcited, but they are not that reducing. They have a redox potential maybe negative 1 volt only. So it is enough to reduce copper-2 to copper-1, but not enough to send the electron to the alkyl halides. So these species, for example, one example here is eosine Y, this is this dye, which can be photoexcited, and then it can react with copper-2 to reduce it to copper-1, and then you have this ATRP equilibrium. Moreover, it has also excellent scavenging possibility for oxygen, the same as copper-1 will be oxidized to copper-2. So you have these reactions of a high molecular weight, low dispersity, and good control. Same with the temporal control. So you have on, off, on, off, on, off, on, off. And of course, with the light, you can have also mask, and you can make various patterns without any evacuation. So previously, you could work only in a dry box or glove box. Here, you can work on the completely open atmosphere. Also very important for bioconjugates, because you can have these 96 well plates and different concentrations, and make bioconjugates with proteins and nucleic acids, which I will tell you on Friday during the last lecture. And again, molar masses or degrees of polymerization up to 1,000, and making block copolymers, good control. Maybe I skip this one. So the last thing, probably from this series, I have still... Yeah, 10 minutes okay. Switching to red light. So this is an example of using porphyrins and phthalocyanins, so in something which would absorb at a red light. And they would be also acting as a dual catalyst, which means that these species can get photoexcited, and then they can send the electron to the copper-2 species to reduce it to copper-1 and start the process of a regeneration. So you need, in that case, also electron donor, because electron donor would be very helpful. And you could see here, you have a reaction of copper with a ligand, and without porphyrin, red light, nothing happens. If you now have all of these three components, polymerization goes nicely. If you have a system which would be larger and higher concentration of zinc porphyrin, in that case you have a faster reaction, always polymers with low dispersity and good control of molecular weights. Another example is methylene blue. So it is also the dye, which would be organic. And in that case, it can have a redox potential in a range of -1 volt. So it can reduce copper to copper 1 and start the polymerization in a proper way. So this is 96 well plates, and you can irradiate with this blue light, or in that case, red light, good control of molar masses and dispersities. So the last example is really showing maybe what normally one would not go this way, how you can heterogenize catalytic system. So this phenothiazine is a very good organic photocatalyst, but it absorbs only in UV light. It doesn't absorb in a visible light. So we try to decorate it with some substituents and also make it heterogeneous so it would be easier removal, and using both green light and red light system in a dual catalytic system. So how is it done? We start with this phenothiazine, which is very inexpensive. It costs probably $10 a kilo nearly, because it's used for something else. And when you start with dimethoxybenzene, in the presence of iron trichloride, which acts as a Lewis acid, you have a Friedel-Crafts reaction, and you get a mess. You get an insoluble system. You have particles of a size, primary particles, maybe sub-micron, and it's very easy to filter, remove it. You have a very large surface area, around 500 square meters per gram. And if you look at this band gap, it would be really corresponding to 550 nanometers, which you could see that it really overlaps with green light and also with red light. So now you can use green light, red light under heterogeneous conditions with a tiny amount of copper. So without copper, you have no control. So this is synthesis of polymethyl acrylate with this dual catalytic system, and you have still tolerance to oxygen as well. So if you look at the table with these results, the system with a copper and ligand 1-to-1, so no excess of electron donor, you cannot reduce it back to the ground state, and there is no polymerization. If you have enough ligand, so excess of ligand, copper is 1-to-1 complex in that case. If you have excess of ligand, which acts as electron donor, polymerization goes to 98, 99% conversion with a very good control. If you have no light, of course, no polymerization. If you have no this phenothiazine, no polymerization. If you have no copper, you have a ligand, you have a polymerization, but you get a 500,000 molecular weight with very poor control, which means you can also a little bit give to the alkyl halide, but there is no deactivation, no control, and practically uncontrolled polymerization. So the last slide here shows really what happens if you isolate this system, because they are of a size, primary particles, maybe micron, but you have a typically aggregated particles of tens of microns, so very easy to remove it. You can just filter it in a simple way, and then run this reaction again and again and again, and same molecular weights, low dispersity, pretty decent control. So I think I probably can finish that a couple of years ago, it was really impossible to dream about reactions in the open bench, because oxygen was making these reactions very difficult. And now you can run these reactions either with this violet light using pyruvate, or green light, or red light, and it has a dramatic difference. In fact, when I was a graduate student like you, I was working with cationic or anionic polymerization. I was doing glass blowing and converting the monomer from one sodium mirror to another one. One experiment typically was like between 3 weeks and a month. And now we have undergraduates in a lab who, after 3 hours training, they can make block copolymers, they can make star polymers, then can make other things. And I think many physicists like you can do these reactions equally well if you know all of these rules. So it's a little bit of a reducing agent, a little bit of the control in water especially, of a halide concentration and some others, but this opens possibility of manipulating macromolecular architecture. And we can go sometimes to systems which would be based on visible light, on this oxygen tolerance, working on a very small scale, making new architectures, going to faster reactions. And here's an example of really going to really thousands of liters and then going to the microliters. So this is done with a printed electrode that you can make a DNA polymer bioconjugates, 75 microliters. You can take a tip of the micropipette. This would be a volume of 50 microliters, so 10 microliters. You can work with this 96 well plate system. So these are really opportunities of making both high throughput system and controlling that in a proper way. So I think I prepared too many slides, so you can ignore whatever is on the web. But